See, in yesterday's class, we were discussing about Faraday's law of electromagnetic induction. Before that, we did three experiments. Can you quickly shall we do a recap of this? Three experiments. In the first experiment, see, in electromagnetic induction, what we are doing is in electromagnetic induction, Michael Faraday and Henry, they did the experiments. Okay, so when there is a current in the wire, around it there is a magnetic field. Okay, when there is a current in the wire, around it there is a magnetic field. So this concept is known as electromagnetism. But now, suppose he thought in the other way, if I am giving magnetic field current, I induce current in the wire. So that was his understanding. So he took a magnet like this and he kept a magnet very close to a magnet or in the presence of magnetic field. But there was no and current was not induced in the current was not induced in the wire. Then later on Michael Faraday came to know that when a suppose he has taken a loop and he connected this loop to a galvanometer and there was deflection. So when you pass the magnet or when you move the magnet very close to the coil or away from the coil, then current is induced in the coil. Okay, that was his understanding. So later on, he came to know that changing magnetic field induces current in the wire. Is that clear, Abid? Changing
Yes, sir.
changing magnetic field induces current in the wire. So that
Current.
was the first statement of Faraday's law. So what is the statement now? The Faraday's law statement says that the magnitude of induced EMF in a circuit is equal to the time rate of change of magnetic flux to the circuit. So the formula is given by E is equal to what? E is equal to minus d phi b by dt. E is equal to minus d phi b by dt. What is phi b? Here phi b is what? Magnetic flux. Okay. Phi b is magnetic flux. Phi b is magnetic flux. So phi b value is how much? Phi b is equal to b dot a. Okay. Phi b is equal to b dot a or b a cos theta. So E is equal to minus d phi b by dt. That is minus. Why there is a negative sign? Because the induced current in the wire is exactly opposite to the direction of the given magnetic field. Exactly opposite to the direction of the given magnetic field. So what is E? E is induced EMF. We are, instead of saying induced current, we are saying induced EMF. So induced EMF E is equal to minus d phi b by dt, where phi b is the flux, and d by dt means time rate. Means we are changing the, suppose there is a coil like this and we are changing the magnet. Okay, we are moving the magnet back and forth. Then what happens? There is current is induced in the wire. So this particular concept is known as electromagnetic induction. If there are n number of turns instead of only one turn in the coil, if there are n number of turns, E is given by minus n into d phi b by dt. So this is the first statement. The first statement that is given by Faraday's law. So second statement is Lenz's law. Okay. The second statement is Lenz's law. Do you have any doubt, Abid? Yeah, any doubt in this?
No.
Yes, Abid. Do you have any doubt in this?
No, sir.
Yeah, okay. Now we'll do a numerical also. Before going to a numerical, I would like to explain Lenz's law and conservation of energy. These two concepts I will explain now first. Then I will go to the numericals. Okay, numerical law based on Lenz's law and Faraday's law, both the laws. Okay. Then we'll do motional EMF also. Clear with you? So to make you understand what is Lenz's law, okay, to make you understand what is Lenz's law, what we are doing here is so just simple example. Just I would like to give a small first I'll write the statement here. Then after writing the statement, I'll tell you a small story so that you will understand what is Lenz's law. So the polarity of the induced EMF. So he says that the polarity of the induced EMF, is such that it tends to produce is such that it tends to produce a current which opposes the change, a current which opposes the change, in magnetic flux that produced it. In magnetic flux, that produced it. Okay, this is the statement of that produced it. This is a statement of what? Lenz's law. Okay, so to make you understand this in a simple way, see, there was a there was a dog which was moving on the road. Okay, this the puppy which was moving on the road. So a nobleman he saw that the dog is going on the road. Maybe it can come under the car and get killed. So he took the dog to his home, gave milk and food nicely, and it grew up. On a sunny day, the dog has bitten the owner and it ran away. Means it betrayed in the simple words. See here now. Now what happened? There is a wire. There is no current in the wire. Now what happened? There is a magnet here. There is a magnet. So this is North Pole and this is South Pole. Clear? So now we are moving the magnet. So if you just keep the magnet, no current is induced. If you keep the magnet stationary and the wire stationary, no current is induced. Now what happened is, now we are moving the magnet back and forth. Okay, we are moving the magnet back and forth. Due to which what is happening? Current is induced in the wire. Okay, current is induced in the wire. When the current is induced in the wire, around it what is happening? Around it there is a magnetic field. Okay, when current is induced in the wire, around it there is a magnetic field. This magnetic field started repelling this magnetic field. Understood now? The magnetic field in the wire, they produced by the wire, is repelling this magnetic field. So, you can understand the story now. Now, who is the dog and who is the owner? Yeah, who is the dog here? The wire, and the owner is what? The owner is your magnet. Okay, so the magnet was the one who induced current in the wire, and because of which the current was induced in the wire, and then there is a magnetic field because of the current, and that magnetic field starts repelling this magnetic field. Is that clear now? Is that clear, Abid?
Yes.
Yeah, so this is about, this is about the Lenz law. Okay, now after that, so we will also, this man, he gave the direction. So what happens if there is a coil? Suppose, see here, he says that there is a coil here, and the magnet here, North Pole and South Pole is there. So this magnet is moving towards the coil. The magnet is moving towards the coil. So what is happening now? So see, a North Pole is formed here. Our North Pole is formed. Means what happens? The current is moving in the anti-clockwise direction. Current is flowing in the anti-clockwise direction. Is that clear? See, once again, when the magnet is moving towards the coil, so he says a North Pole is formed, and the induced current is in anti-clockwise direction. The current is in here in anti-clockwise direction. Now the second one, what he says is, this is a North Pole and this is South Pole. The magnet is moving away. Now in this loop, the current is flowing in the south, in this way. The current is moving in this way. Is that clear? The current is flowing in this way. See, in the south, in this one, when the magnet is moving away, a South Pole is formed, and the induced current is in clockwise. The induced current is in clockwise. So he explained how conservation of energy. Now, how can you explain that? He says that a North Pole is here. In the first case, a North Pole is formed, and in the second case, South Pole is formed. So here, then the people asked him, how will you explain this? Okay, why not South Pole here, and why not North Pole here? So people asked him the question, how will you explain this? He said that, okay, this is said to be conservation of energy now. Okay, Lenz law and conservation of energy. This question came in the board exam also. Okay, so one of the important questions, especially the reasoning how it works. Now, and then I will explain you. I will give some circuits after that with the Lenz law. If they give the statement in the examination, they ask like state the Lenz law and explain the following circuit given below. Explain the polarity. Explain the polarity given below. Okay, I'll draw some circuits down after that. Then you have to tell me whether a north pole will be formed, whether a south pole will be formed, whether the current will flow in the clockwise or anti-clockwise. That you have to explain now. Now, see here what he says. Suppose when a north pole of the magnet is moving towards a coil, what happens? Current is induced in the anti-clockwise and a north pole is formed. Simple way. See here, I am taking a right hand thumb rule. Right hand thumb rule, what he is saying, if the thumb indicates the direction of the current, then the curled finger shows the direction of the magnetic field. Once again, if the curled finger shows the direction of the current, then the curled finger shows the direction of the magnetic field. Now in electromagnetism, the same concept was explained in a different way. If if the curled finger shows the direction of the current in a coil, then thumb indicates the north pole. This indicates the north pole. Same way, see here, if the current is flowing in this way, then this is the north pole. See here, is it clockwise or anti-clockwise? This one, when you look from there, from your end, this is it clockwise or anti-clockwise? This one, this anti-clockwise. If whenever there is an anti-clockwise, are you there, Abid? Are you there, Abid?
Yes, sir.
Yeah, is it clockwise or anti-clockwise? This one, this direction.
Anti-clockwise.
Anti-clockwise. Whenever there is anti-clockwise, there will be an north pole. Is that clear? So same thing has happened. Whenever the current is in the anti-clockwise, a north pole is formed. Now see here. Now here, see, current is moving in clockwise or anti-clockwise now? Clockwise, right? Current is from your end, not
Yes, sir.
from my end. It is clockwise. Whenever the current is
Clockwise.
clockwise, then a south pole is formed. So that's the reason. Okay. Now people asked him. Now people asked him. So how can you prove that? Okay, until there it's clear. But okay, when there is a current in the coil, you are saying you are able to say there is a north pole. If the current goes in this way, you are saying when the current is flowing in this way, there is a north pole. When the current is flowing in clockwise, then there is a south pole. Okay, that's well and good. But why? What about the magnet? When the magnet is approaching the coil, you're speaking about the magnet approaching the coil. Then he said that. Then he took contradictory statement. Means instead of a north pole, a south pole is formed. Example. In both the cases, he took the contradictory statement and he explained this one. He said instead of north, think that for some time, think that a south pole is formed. What would have happened? If south would have happened, then what happened? The north pole will attract south pole and it will pass through the magnet. It is violating the law of conservation of energy. So that is why they have given conservation of energy there. Got it? So once again, suppose the south pole is formed here. What will happen? North pole will get attracted to the south pole, then it will pass through the coil. Means what? Without giving any energy, okay, without taking any energy, it is even easily passing through that one, which is violating the law of conservation of energy. Now, is this clear? The first one, Abid?
Yes, sir.
Yeah, coming to the second one now. Coming to the second one, he says that suppose a magnet is moving away from the magnet and a south pole is formed and induced current is in the clockwise. Now again he said that think for some time, think it is a north pole. For some time, here this will become a perpetual machine. The first concept is like perpetual machine. You know what is perpetual machine? Perpetual machine. You know that?
No.
Perpetual machine means without any energy. Perpetual machine means without any energy. Without any energy, it starts working. The machine starts working by itself. So that concept he told here. Magnet, if suppose a south pole is formed here, magnet will easily pass through without taking any energy. Means I'm not even applying any force. Magnet is easily passing through the coil. So that is giving the concept of perpetual machine, which is not possible actually. Now, means without taking any energy, the machine is working by itself. That's the meaning of it. Now, suppose in the second case, instead of a south pole, a north pole is formed. In the second case, a north pole is found. What would have happened? Before the magnet is repelled, see what is happening. We are moving the magnet. So instead of moving, we are moving the magnet. The magnet is still moved by itself because of repulsion. Here we are doing physical experiment. This magnet, I am taking the magnet, I am going towards the coil. I am moving the magnet away from the coil. But without moving the magnet is coming by itself. Magnet is moving repelled by itself, which is again violating the law of conservation of energy. So that is why they wrote Lenz's law and conservation of energy. Is that clear? Is that clear?
Yes, sir.
Yeah. So this is about one of the important concepts. Okay, write down this one. Then we can quickly go to the okay. Then we'll quickly now. I would like to do some experiments. Okay, I would like to do some experiments on some numericals. Okay, not experiments. I'll do a numerical on this. Then quickly after doing the numerical, we can go to the we'll go to the motional EMF. Is that clear? Is that clear all of you? Okay. So example 6.2. Okay, example 6.2. So we have example 6.2. Okay. Now, in the example 6.2, he says that a square of loop of side 10 centimeter. There is a loop. Instead of a circular loop, there is a square loop. A square of loop 10 centimeter and whose resistance? The resistance of this loop is 0.5 ohms. Placed vertically in the east-west plane. The vertical is east-west means this is east and sorry, this is west and this is the east-west plane. Okay, in this way. Uniform magnetic field, how much is the magnetic field? B is equal to 0.1 Tesla. Is set up across the plane in the north east direction. Means what? Suppose this is north, that means northeast direction, like this. The magnetic field is set in this way. Okay. So northeast direction. So now he says the magnetic field is decreased to how much? Initially to 0. So this is B1, B2. B2 equal to 0 Tesla. In how much time? Time t is equal to 0.7 seconds. Determine the magnitude of induced EMF. How much is the induced EMF and how much is the current in the time interval? Okay. So we know that. What is the formula? Now this magnetic field is making an angle with the plane. Suppose the plane is like 1 second. So I would like to explain this. So suppose this is a square loop. There is a square loop and the magnetic field is given at this angle. Okay, 45 degrees. Okay, 45 degrees means the plane is he said northeast. Okay, like this. Magnetic field is cut in this way, and the plane is like this. Now, so what will happen now? Now we have the formula. What is that? Phi is equal to B into A cos theta. Okay. The flux phi is equal to what? Flux phi is equal to BA cos theta. Okay. So in the first case, what will happen? 0.1, 0.1 into area. Area is how much now? Area is 10 centimeter. Instead of taking 10 centimeter, we are taking 0.1. Okay. 0.1. And theta will be how much now? Theta is 45 degrees. The angle between the material, the loop, the square loop, and the magnetic field is 45 degrees. Is 45 degrees. Now, flux is how much? Phi is equal to B dot A cos theta in the first time. So flux phi is equal to B dot A cos theta. So 0.1 into 10 to the power of minus 2 by root 2. So here B dot A P is magnetic field how much? 0.1 into 10 to the power of minus 2 into cos 45 is 1 by root 2. Okay, cos 45 value is 1 by root 2. Okay, this is the value. This is phi 1. This is the flux. This is the flux phi 1. Now, that is in Weber, or we can Weber. This flux is measured in Weber. So the second one is what? The flux phi 2 is equal to 0. Why? Because the magnetic field becomes 0 in the second case. Flux phi 2 will become 0. Now the third, what is the next one? The next one he says, one second. So what he says, the magnetic flux is 0. So E is equal to what? E is equal to minus d phi b by dt, or delta minus d phi b by minus d phi b by dt. This is the value. Okay. This is the EMF. So how much it will be now? So we have into dt by dt. Okay, change in time. So E is equal to how much? E is equal to minus 0.1 into 10 to the power of minus 2 by dt. Dt is how much? Root 2 into t. What is t? The time period is 0.7 seconds. 0.7. Okay. Which is equal to what? E is equal to what? 1.0 millivolts. Okay. E is equal to 1.0 millivolts. So I is equal to what? The formula for current is I is equal to E by R. Induced EMF by R. So I is equal to how much? 1.0 millivolt divided by resistance. What is the resistance here? 0.5 ohms. So I is equal to how much now? I is equal to 2 millivolts. Okay, 2 milliampere. Is that clear? 2 milliampere. See once again. He said the magnetic field is changing. So how do we get induced current whenever there is a changing magnetic field? He said initially the magnetic field is this much, and the wire has having length 10 centimeter. It is in the form of a square, and his resistance is 0.5 ohm. And second magnetic field slowly it is coming to rest. Earlier the magnetic field was more, and slowly it is changing. The magnetic field is changing to 0 in 0.7 seconds. It's not even 1 second. It's having quickly. So current will be induced in the coil. So when the current is induced in the coil, okay, so current is induced in the coil. So he's asking how much is the induced EMF and how much is the induced current. So we have the formula phi is equal to B into A cos theta. So the first one substitute the formula, second time it is 0 because B is 0, and E is equal to minus d phi b by dt. That is rate of change. So no need to get confused with this. So here we can also write minus delta phi b by dt. Okay, change in the flux by change in time. Just substitute the values, we'll get the answer. So I is equal to what? E by R, then we'll get the answer. Is that clear with you? Yes, Mr. Abid.
Yes, sir.
Yeah. Okay, so shall we go to the next question now? We'll try one more question. Okay, one more question on this one. Yes, Mr. Abid, is it clear now? This numerical?
Yes, sir.
Okay, so we'll go with the second one. So now here the second next question is example 6.3. Okay, example 6.3. He says that example 6.3. So please learn the example questions also, including the exercise questions. Okay, that is enough. Okay, for the exams, and I can do some past paper questions also. He says that a circular coil of radius. How much radius is given here? R is equal to 10 centimeter. How many turns? 500 turns. Okay, it has the coil has 500 turns. And resistance is equal to how much? R is equal to 2 ohms. R equal to 2 ohms is placed with its plane perpendicular to the horizontal component of Earth magnetic field. Okay, resistance is placed. The circular coil of radius 10 centimeter, 500 turns, and resistance 2 ohms is placed perpendicular to the horizontal component of Earth magnetic field. See here, this is the Earth magnetic field, B. This is the horizontal component. BH is the horizontal component, and BV is the vertical component. And this is the theta angle. Okay, horizontal component of Earth and vertical component. Like suppose when you suspend a magnet freely, so what will happen? The magnet will be slightly tilted. So what will happen? There are actually because of the north pole. This is because of the magnetic north pole being down. So now this is the horizontal component and this is the vertical component. So now here the coil is placed in the horizontal magnetic field. Now it is rotated about its vertical diameter through theta is equal to 180 degrees. How much? Angle is equal to 180 degrees, and then angle is 180 degrees. And also he also says that when time t is equal to 0.25 seconds. Okay, this is definitely that should be given to you. Time should be given to you, or you have to sometimes find out the time. Estimate the magnitude of the EMF and the current induced in the coil. He is asking us to find out what is the EMF and what is the current in the coil. Okay, he is asking you to find out what is the what is the induced EMF and what is the current. What is the induced EMF and what is the current in the coil. Okay, so now horizontal component of Earth magnetic field is given to you, that is 3 into 10 to the power of minus 5 Tesla. So magnetic field is also given to you. See, 3 into 10 to the power of minus 5 Tesla. Generally measured in Gauss also, so that is given to you. Now, first we'll find out the magnetic flux. Initially, what was the angle here? Now, here instead of changing magnetic field, we have theta 1 is equal to here. This is theta 2, and this is theta 1. Theta 1 is equal to 0 degrees, and theta 2 is equal to 180 degrees. Okay, so theta 1 is equal to how much? D into A. So theta 1 is equal to what? D into A cos theta. D into A cos theta. So theta 1 is equal to what? D is how much? Magnetic field 3 into 10 to the power of minus 5 Tesla. And area, what is the area? This is a circular coil. Circular coil means the formula is pi r square. The area formula is what? Pi r square, area of a circle. So pi r square, pi into 10 to the power of 10 centimeter means 0.1 whole square, 0.1 whole square into cos 0 degrees. What is cos 0 value? Cos 0 value is 1, and cos 180 value is minus 1. Okay, that is equal to minus 1. Now here we'll simplify this one. That will become how much? 3 into 3.14, 3.14 into 0.1 into 0.1. That will become 0.001 or 1 by 10 whole square. 1 by 10 square. Okay, into 10 to the power of minus 5 into 1. And phi 2 is what? Phi 2 is equal to how much? The second flux. So that will be minus 1. Same value 3 into 3.14 into 10, 1 by 10 square or 1 by 100 into 10 to the power of minus 5 into minus 1. Cos 180 is minus 1. Now simplify that value. Same value, but it is different. Okay, E is equal to what? The formula is E is equal to, first we have to calculate E. E is equal to that is n into d phi b by dt. N into d phi b by dt. Change, okay. N is how much? 500 turns. N is 500 turns. D phi b by dt is how much now? D phi b by dt is equal to how much? So it is equal to what? 3 pi, 3 pi. Okay. So that is equal to how much now? That is equal to 3.8 into, that is 500 into 6 pi into 10 to the power of minus 7. 6 pi into 10 to the power of minus 7 divided by dt. Dt is how much? 0.25. 0.25. E is equal to how much? E is equal to 3.8 into 10 power minus 3. 3.8 into 10 to the power of minus 3 volts. Okay. And what is I? I is equal to E by R. I is equal to how much? E by R. E is 3.8 into 10 to the power of minus 3 divided by the resistance. Resistance is 2 ohms. So the answer is how much? 1.9 into 10 to the power of minus 3 amperes. Okay, milliamperes. That much is the current induced. Is that clear now? Abid? See, once again from the beginning, there is a circular coil whose radius is 10 centimeter and it has 500 turns, whose resistance is 2 ohms, is placed in the horizontal component of Earth magnetic field. And first, what happened? It was at 0 degrees, like the coil was like this, man. The coil was like this. So what happened? 0 degrees. Now they turned it like this. In how many seconds? Like this, one turn. In how many seconds? In 0.25 seconds, from 0 degree to 180 degree. Then he is asking how much is the current induced. Okay, clear? So first we have to find out the area first, and theta is 1 degree, cos 0 and cos 180 values are given. This is a magnetic field and flux. First one, here you will take 0 degrees. For the second term, 180 degrees. Then E is equal to N into d phi by dt. Just